So in this video I want to discuss the complexity properties of Shellsort. Unfortunately, there's not much to discuss. The complexity properties of Shellsort are in the majority not clarified, so there are many open questions left. So it's not very clear what the accepted growth rates of Shellsort with respect to average case and worst case are. So there is no fixed answer to this question. So what we can say is that the best case is quite clear. Again, it's the array which is already sorted, and it's not as cheap as insertion sort, which only takes n many steps to check whether the array is already sorted. But it takes k times n many steps, and k is the number of h values that are defined in Shellsort. So k times n is just an upper bound for the number of steps. So in practice, you will have less than. But what you see is in the best case number of comparisons in case of Shellsort is just linear. However, one question is here: what the heck is the worst case of for Shellsort? It's not very easy to find out, and there are so many other questions like what is sequence of which sequence of increments is optimal. So there's still it's still possible that one can find values for h, or a sequence of h values which is better than the given ones. So if you try to find out what the complexity of Shellsort is, well, then you can what you can do is a simulation. So in this tool here, I do some simulations, and actually I did this here for Shellsort, and what you see is the results of Shellsort. So here on the x-axis you have the array size. So this diagram now ranges from 128 to 2 to the power of 11, and here is the number of comparisons needed. The blue lines here are very important typical growth rates. So this is n times log 2n. And this is more or less n squared half, and this is n squared. And what the red dots here are the simulation results achieved by Shellsort. So if I just stop it here, what you see there, this line here just says, okay, we are at a certain size of array size. So this is 1,570 elements, and we made 3 experiments with this array size, and you see the number of comparisons needed in the minimal case. So the best case seen so far is this number, the worst case seen so far is that number, and the average is that number. So if you have a look at the position of these dots here, well, you see it's above n times log 2n. It seems to be twice as 2 times n times log 2n, roughly, but nobody knows precisely. Nobody can come up with a proof for this. So I did this for these values, and if I just increase the upper bound for this in a simulation, then we see that there are even more results. So here we are, and you see if these red dots always mark this the average of the simulation results, and it seems that is 2 times log 2n. Here, if for very small array sizes, we can find out the precise values. If we zoom in, you see that these dots become bars, and the meaning of such a bar is so that the dot in the middle is the average of all simulation results, and this is always the minimal value, and that is the maximal value. And you see for an array size of 10, it actually, here we have 10. Well, it makes for array size of 10 elements, you need roughly 3.5 million experiments, and the best case is 90 comparisons, the worst case is 37, and the average is 27.4. Yeah. So that's there's always a span or a range of between worst case and best case, obviously, and it's. But if you look at larger values, you see it seems that it comes close to 2 times n times log 2n. Yeah. So, but nobody knows this precisely. So there's still a proof missing here.